In today's 3 steps to sketch, we'll graph a shifted cosecant graph. So we're looking at y equals 3 cosecant of 2x minus pi over 4 plus 1. So you can tell there's a lot of shifting going on here. And let's go ahead and jump in to look at the method, and we'll analyze this in great detail. So here's our method that we know we'll use for shifted cosecant equations. And remember, the general form for a shifted cosecant equation is y equals a cosecant bx minus c plus d. So we can tell we definitely have these shifts going on here. We have factored out 2. If you feel comfortable writing it out as 2x, just distribute that 2x minus, and then 2 times pi over 4, of course, is just pi over 2. You can do that, but I do like it written in this format as well because I think it's easy to see the phase shift. It's already kind of factored out for you, but we'll talk more about that in detail in just a few moments. All right, so a quick overview of the steps. In step 1, we do the bulk of our analysis. We find a companion equation. The companion equation is always going to be its reciprocal function. So in this case, sine is the reciprocal of cosecant. We'll do all of that analysis, find the essential information, so that in step 2, we can plot that companion pattern and do our shifts. We'll mark that in a different color or mark it lightly because that is going to be the basis for step 3, where we create our actual graph. So we will kind of transform our companion pattern into our reciprocal graph. We'll sketch in the graph and then repeat. All right, so step 1, let's write out our companion equation. All you have to do is replace cosecant with sine. So y equals 3 sine, and then we have 2x minus pi over 4. Remember, you can keep that distributed, 2x minus pi over 2 if you want, plus 1. And just a quick note before we do too much more, this is a great method to use if you're really comfortable graphing shifted sine graphs already, because there's really just that one extra step at the end to create the reciprocal graph. You can also do this graph as a transformation of the parent function cosecant, but that can tend to get a little bit complex. And I like the analysis with this method because we actually go through, for example, finding the period, talking about the shifts in detail, finding the asymptotes, things like that. But you do have an option there. All right, so really digging in now, let's analyze this base graph. So a is the leading coefficient, or that coefficient in front of sine. So a is 3 in this case. That's going to help us set our maximum and minimum for our companion sine pattern. Okay, we'll do that in step 2. B is the coefficient of x, so that's 2. We'll have 2 cycles of our graph that happen between 0 and 2 pi, and we can also use b to calculate the period. So remember, that's 2 pi divided by b, so 2 pi divided by 2 is pi. So pi is the length of one horizontal cycle. Now we can choose scale labels. And so when choosing a horizontal scale label, I always take my period and divide by 4 so that in step 2, each of the 4 points in the companion pattern will align nicely with your tick marks. Of course, that's before you shift, but it's a really good starting place. So take your period, divide by 4. We'll count by pi over 4 when we label the horizontal axis. And for our vertical axis, we'll count by 1 here. So let's label our grid. Starting with the horizontal, count by pi over 4, 1 pi over 4, 2 pi over 4 reduces to pi over 2, 3 pi over 4, 4 pi over 4 reduces to pi, 5 pi over 4, 6 pi over 4 reduces to 3 pi over 2, 7 pi over 4, and 8 pi over 4 is 2 pi. All right, so I'm going to pause. If you're following along, pause as well. That way we can get the negative side of this axis labeled. All right, so you can see now I have the left side of the horizontal axis labeled. It's all the same values as the right, of course, just negative. And now let's label our vertical axis counting by 1. Easy enough. And now we're ready to talk about our shifts. So C over B will give us our horizontal or phase shift, and D is going to be our vertical shift. So D is very straightforward. We see that plus 1 after the parentheses at the end or the right end of the equation. So positive 1 tells us we're moving our base pattern for our companion graph up 1. Now C over B. We want to make sure we have a minus sign in our particular equation. We do. Sometimes that will, if you see a plus, that's actually minus a negative, so that can trip some people up. But when we have this factored out form of the equation, let's look back over to our original equation. That right there, we actually can just zero in on the inner parentheses, and we know that our phase shift will be right pi over 4. The reason that works, look back over to the general form now, is if we factor out b, we're left with x minus c over b. And so that c over b should look familiar. That's what we said is our horizontal or phase shift. And that's why we can just simply look at the original equation and know our phase shift is pi over 4. Okay, if you don't like that, if you wanted to keep it as that 2x minus pi over 2, you'll see that if you do pi over 2 divided by 2, or times 1/2, you'll get the same result. So we know that our phase shift is positive pi over 4, or we'll shift right. Okay, so now our final bit of analysis before we jump into our graph. We want to find our asymptotes equation. And so there's a really easy way to do this. I have some videos on this. Look at the link for cosecant graphs in the video description if you want to check those out. But for this particular example, I'll just go through it pretty quickly. We're going to take our inputs of our cosecant function. So that's 2x minus pi over 4. And we're going to set them equal to the parent asymptotes of cosecant x. So that's 0 plus pi k. Okay, so writing that out here, just doing some scratch work, we have 2x minus pi over 4 set equal to 0 plus pi k. And we do this because we want to find all of the asymptotes. We're essentially taking the parent asymptotes and applying all of the horizontal transformations to them. And that's because vertical asymptotes are only impacted by horizontal transformations. Okay, so check those videos out if you're interested in even more details. But for now, all we need to do is solve for x. So let's first start by dividing everything by 2. So on the left side, we're left with x minus pi over 4. Of course, 0 divided by 2 is 0, and now we have plus pi over 2k. And then all we have to do is add pi over 4 to both sides. And notice that when we do that, the only like term on the right side is that 0. Pi over 2k is its own type of term, so we do not actually have to combine those two. All right, now I'm going to write the final asymptotes equation over in its place. So x equals pi over 4 plus pi over 2k. And remember, k is simply an integer, and depending on what integer you substitute in, you'll get a different asymptote along the graph. So I like to find this equation in this analysis step because it acts as a confirmation of my final graph. So I'm already expecting asymptotes. For example, let k equal 0, I'm expecting an asymptote at pi over 4. If you let k equal 1, we should know there's another one at 3 pi over 4. When k equals -1, we're expecting an asymptote at negative pi over 4. So play around with that. Get really comfortable with substituting in different values for k and locating these different vertical asymptotes. All right, now we're ready for the fun part, the actual getting the graph on the grid. So in step 2, we're plotting our companion pattern and then we're shifting. So we're going to have effectively 2 intermediate graphs or companion graphs here. Plot these lightly or with a different color. So I'm going to use light blue. Okay, so we know that the companion graph sine typically follows the pattern starting at the origin, x-intercept maximum, x-intercept minimum. Okay, so that's how we'll work here. Plot lightly starting at the origin. We have our first 0. We purposely designed our scale. We divided our period by 4 so that each of these points would align with horizontal tick marks. So move over to pi over 4, that first horizontal tick mark to the right. That's where our maximum will happen. And to get the y-coordinate, just look at the value of a. All right, next x-intercept happens at the next horizontal tick mark. So at pi over 2. And then 3 pi over 4, our third horizontal tick mark, will be the minimum. The y-coordinate's just the opposite value of a. All right, so you can kind of see that sine curve forming. And now we're ready to shift. So as I mark this next intermediate graph, I'll use x's. So all we have to do is shift each of these points to the right pi over 4, so that's equal to 1 grid unit based on this graph, and also up 1 unit, so 1 vertical grid unit. So let's do each of these one at a time. We can do 2 steps in one. So starting at that point, that first point on the origin, move right pi over 4, and then up 1. So that new first point will be at pi over 4, 1. So just move each right pi over 4, up 1, right pi over 4, up 1, right pi over 4, up 1. All right, so you can see this sine curve happening here. And this will be what we work from to create our reciprocal graph. All right, so in step 3, we're not taking literal reciprocals here. We are just transforming each of the points from the companion graph into its corresponding cosecant point. Okay, so the original x-intercepts, they're now with a y value of 1 since we shifted up. Those turn into vertical asymptotes because if you try to take a reciprocal of 0, of course that's a vertical asymptote. Okay, so we'll have vertical asymptotes here and here. Notice that's at pi over 4 and 3 pi over 4, and that's when we let k equal 0 and k equal 1. So we should be feeling really confident about this graph so far. All right, then the next translation we make, we turn our maximum from our sine companion pattern into a local minimum. So I'm going to go ahead and sketch the curve in here. That's your local minimum for that part of the cosecant curve. And then finally, we have our minimum from our sine companion pattern. That turns into a local maximum with this part of the cosecant curve. So here you have one cycle of your cosecant graph. So now we can go ahead and repeat this pattern over and over again until you have as many cycles as you want. All right, so we start out first with a vertical asymptote here at 5 pi over 4. You're probably guessing this, but that'll be the asymptote that you get when you substitute in k is 2. All right, you have a local minimum here at 3 pi over 2, 4. Another vertical asymptote. That one will come when k is 3. And then a local maximum and sketch in that curve. All right, and let's work backward. So we're just repeating this pattern over and over again. We have that local maximum, vertical asymptote. We talked about that one as well earlier. That's when k is -1. -1. All right, so then of course we have a local minimum, vertical asymptote. That's when k is -2. Local maximum, asymptote when k is -3. Local minimum, asymptote when k is -4. Local max. So sketch in those curves, and you've got a really nice sketch of a pretty complicated shifted cosecant graph. So hopefully this helps you see how you can use the 3 steps to sketch method to tackle a complex shifted cosecant graph. One thing you can look back and double check, we already talked about the asymptotes, but remember B, we said told us how many cycles of our graph should happen between 0 and 2 pi. And here you can see you have 2 cycles that happen there. So that's kind of a neat double check as well. Like I said, hope this really helped you out, and you can apply this method to any shifted cosecant graph. Check out the links in the video description, and I'll also post how to graph other trig functions as well. Thanks for watching.